All right. And I'm happy to introduce Nathan from Chalk, who's going to be talking about real-time ML with, I can't see your, sorry. You can do quit. Accelerating Velox and Python. All right, thank you.
I'll use this. Hi, I'm Nathan. I'm a software engineer at Chalk. We're a small startup that's working on a compute platform that makes it easier for smaller teams to develop large-scale feature pipelines. Basically, the problem we're trying to solve is making it easier for teams without lots of infrastructure experience and query planner experts, like everyone here in the audience, to ship models fast and incorporate new data sources. Oftentimes, teams end up having to do complicated ETL pipelines just to get data that they want to add to their database, even though they know another database that they use all the time and is perfectly capable of serving stuff on demand is used for other products outside of machine learning. And this is important because they want to be able to react to real-time signals. If you're looking for patterns of fraudulent behavior, knowing what happened yesterday is not going to be any good at spotting 10,000 fraudulent transactions created over 10 seconds. So what Chalk does is we compute your data on the fly so that your features come from whatever their original data source is, whether that's SQL or some API that a vendor provides, or derived from other feature values that you also want to keep up to date. So we do this with a bunch of things that we call resolvers, which are blocks of computation functions that are made of SQL, APIs, Python, or whatever else you might want to build, that we then stitch together automatically to serve both online and offline queries. Of course, the distinction here is important because online queries need to happen in response to user actions. And so this is someone makes a payment or they click on a link and you want to show them recommendations. And that means that you need to respond quickly. So low latency, like less than 100 milliseconds, so it's roughly instantaneous, is an ideal target. But you want to do this rapidly, hundreds of queries or thousands of queries per second, which is very different from the training offline case, where you're trying to build historical data at high row cardinality with larger than memory workloads. But what a lot of teams struggle with is because the performance characteristics are very different for these two kinds of systems, they end up building the system twice. This makes it hard to evolve the system because whenever you want to add a new feature, you have to go update it in two different places that behave very differently. So what Chalk is doing is we're using Velox as a common compute engine for both offline and online queries. So in this talk, I'm going to just focus on online because we've had lots of talks about scaling offline to billions of rows. So this makes productionization a lot easier because you write it once after your experimentation and it's ready to go. We manage the configuration automatically with lots of helpful tooling. So here's what it looks like. We want to define features declaratively so that we're able to look them up later beyond just a bunch of SQL tables or a bunch of workhead files. And so we do all of our configuration as Python code that we ship as one large unit and do analysis on to build a feature graph. So it's just a Python class with an annotations of @features at top as a decorator, and then we read all of the types in order to produce an arrow schema for this, whatever this class is. This allows us to do basic features, float strings, but also more complex ones like lists and maps and structs. And it also lets us define relationships between different features. And this is really useful for making it possible to evolve your data over time. So in this case, for example, we see that every transaction belongs to a user, and every user has many transactions that it can access through a data frame that contains them, or in particular, contains whichever columns of them it wants to use. So resolvers are how we actually compute those values. And the most common kind, because SQL is king, are SQL resolvers. We're able to just define a SQL file that resolves some subset of the columns of any particular feature class. In this case, we have one that selects 3 different columns from some Postgres table to resolve those fields in the transactions table. But we're not we're not restricted to one database at a time. We can also have a BigQuery table that resolves some other set of columns. And in particular, if we only need some of them from one of these two places, we know in advance where we need to get them from. But if we need both, we can just pull from both and join them on the fly. This is sort of like the feature insertion process that the Metalike talked about yesterday, in that we're just stuck in the slow case where we're still constantly pulling from 2 different data sources, but we find that we can get this to be more than fast enough to serve our users, and it gives them much more flexibility because they're able to instantly add or remove any feature column that they want from any data source. And since these are just SQL, we're still able to do SQL pushdown. So we execute these primarily as UDFs inside our existing Velox plan. And so this allows us to easily support any number of databases from Postgres to SQLite to BigQuery, etc. And the other big kind we have are Python resolvers. And so Python resolvers are just Python functions with annotations on the inputs and outputs that tell us which features they represent. So for instance, we might have a get user from API that takes in a user's ID and returns their name and email, or we might have something that takes in the recent transactions amount category with a filter on the date being recent, and it will return the user's recent transaction volume using some kind of formula that the user defines. But these are really arbitrary Python. So of course we can do like data frame pandas style operations or polar style operations where you take in some data frame and do that. But you can also just like throw in an HTTP request or have a stateful client or whatever else that it is you want, because we're really running Python in order to load whatever this data is. The other thing we have is we allow for easy point-in-time historical queries and easy cached values for the current data. And so you can simply attach a max staleness to any feature value to indicate, oh, here's how stale I'm willing to allow this feature to be. Then when you want to load it, we will first look in the online store to see, oh, does it exist in this Redis cache? And if so, we can skip running whatever resolver and whatever inputs that resolver might need and just deliver the value immediately. And so you can take something that, say, is fresh 99% of the time and then vastly reduce your cardinality and therefore reduce your latency in loading it. So our query planner basically looks like a sort of traditional build system in that we have a list of output features that we're looking for, and then we're going to sort of go backwards through the resolvers that are available, finding the ones that resolve those features. And while we do this, we're also looking for relationships across them so that, for instance, if you want, the user wants the transactions table and the transactions has derived fields that come from some other table, we will continue going down looking for more resolvers until it eventually resolves everything. So here's an example in our web UI of what like one of these query plans actually looks like. So this is like 10 plus Python resolvers, 5 different Postgres lookups, 2 different Redis online store lookups for different namespaces, and this whole thing ran in 68 milliseconds in one of our dev clusters. So it's pretty straightforward to sort of add and remove any number of features that you might want to load, which makes the developer experience for this really nice because it's very declarative, it's very easy to change things. And so, of course, we're actually executing that on Velox. So each of those little boxes expands to one or more Velox operations. Sometimes it's just turning a Python call into a UDF. Sometimes we're doing a join. Sometimes we have to apply extra filters in order to make point-in-time queries correct. But we're able to sort of expand this into this much larger plan that we're then actually running. And again, this particular one ran in 68 milliseconds. And so here's like a zoom view, so we can see some of the like common operations that happen. We've got like a UDF that is actually performing an online store lookup from Redis. We've got some joins, we've got some projects, all very like standard operations. And so we have a bunch of optimizations that we've applied on top of Velox in order to make it better at doing these sorts of online queries. And so one of the big things is we have replay. Because we have resolvers, which are potentially very slow, we want to avoid running them multiple times. And so while we run them, we record any data that we might need effectively as a materialized CTE. We call this replay, where record batches that are going to be needed twice, such as this SQL result here for 2 different parts of the plan that we want to run concurrently. It will be duplicated into a replay network so that we don't have to compute any of those values twice. And it also counts how many times they're needed so that it doesn't hold them onto them any longer than is necessary. And this is important that it's in memory for the online queries, because otherwise we would have to spill, which would mean copying, which would mean extra latency. And so all of the record batches are typically held in memory until they're going to be needed. Another kind of optimization we find is that we have a lot of hash joins in our plan because we're doing replays to avoid duplicating resolvers, but that means we eventually have to combine the data back together. And what we found is that the Velox's hash join on the build side converts from a column format to a row format because it needs to store each of the rows into a hash table so that spilling is possible. However, we don't want our online queries to spill because that would mean touching disk, which would be very slow. So we have a custom online hash join, which is essentially a fork of the original hash join, which is optimistically 0 copy. It keeps the original build side record batches in memory so that it can select individual rows from them instead of needing to copy, and we found that in end-to-end in one of our like typical queries, this was 1.4 times faster. The other big thing that we've done is we've noticed that when we have very low latency targets, like say 50 milliseconds or less, a significant portion of time is spent on Velox analyzing the expressions in the plan. So some plans will have like 10,000 expressions, which isn't that many, but if you spend a microsecond per expression, that ends up adding to multiple milliseconds of overhead. And this will run every single time you want to run the query before you even have the data to run it. So on one particular giant query, we saw that 50% of the CPU time that it was spending was spent just on expression initialization before it was even looked at the data for those expressions. We were able to reduce this by 17% just by caching expression equality and rewrite rules. We were finding that it would repeatedly compare the same expressions over and over to each other, even though they're not changing whether or not they're equal, and it would apply rewrites that don't go anywhere. So by caching this, it was 17%, and we got this even lower by caching expression set initialization completely. Every project and filter has a expression set that has been expanded into a pool of already initialized expression sets. Whenever a new query comes in, it will reuse one of those initialized expression sets or create a new one only if they weren't already available. Lastly, we run a lot of Python because we want to make it really flexible and easy to define new features and new derivations of features that are going to go beyond whatever our ideas of the operations that you want to perform on your data. Our customers always have their own ideas. So every Python function has a strict arrow schema for input and output because we know what the feature classes are, and so we just have to convert from Velox to arrow to Python to arrow to Velox and back in order to be able to run them. This is a little bit inefficient, but being able to use arrow as a common format makes it a lot easier to interop with the existing Python tooling. And to actually run them, we have a pool of subprocesses that receive requests for chunks of the input record batches that we receive and run them in parallel. But in practice, this is great for flexibility. It's really easy to define. New ones, engineers and data scientists like reading them, but they're really slow. And there's lots of reasons that Python is not as fast as Velox, which should not be surprising. It struggles to run multi-threaded code. It has heavy type representations because of dynamic types. Every int and string and float is going to be a heap allocated object. And obviously, it can't do simd if you're writing a bunch of operations that take one value and add it to another one. But who are we to say that our users shouldn't write a plus b as a Python resolver? So we have Velox. It solves these problems. What we've done is we've noticed that a vast majority of the Python resolvers that people write are really just doing basic data cleanup and transformation. So they'll check, for instance, in this case, that the discount is not none, and if it is, then they'll modify one of the other values by reassigning some basic functions. They'll have an early return or some various checks for edge cases. And ultimately, they're usually doing arithmetic or string manipulation or array manipulation, etc. And Python is really nice to write this. It would be annoying to write this, for instance, in SQL. You totally could, but it's not what people would usually reach for this kind of transformation. So our breakthrough is that we have a symbolic Python interpreter. At query plan time, we look at all of your Python UDFs, and if one of those UDFs has the form of one of these pure compute operations, we will convert it into a Velox expression directly, so that at runtime, there's no Python involved. And the way we do this is what I'm going to go over now. So basically, we have an environment that stores a mapping of each Python variable name to the corresponding underlying Velox expression, along with metadata, which describes what the Python type would be if we were running Python. So initially, these are going to be column expressions corresponding to whatever column we happen to be running. So for instance, the discount we know comes from some column, say, named D, and subtotal comes from S, etc. And these will refer to the original value that was plugged into the Python value. So when we have a Python expression, we just have to evaluate it like we would if it were Python, but we replace the result with a new Velox expression that does the same thing. So for instance, a Python subtraction, we look up the corresponding values. They're both float types, and so this means we'll just be able to use plain old Velox subtraction on the results, and it would produce a Python float. And so we're able to then take this value and do more things with it. For example, if we have a reassignment, we just evaluate the thing on the right into whatever the corresponding expression would be, which in this case looks exactly the same, and then we replace it in the environment. So all the other variables hold their old symbolic values, and the one that was reassigned, in this case, whatever x equals y, the x value is replaced with a new symbolic value. And for if statements, it starts being a little bit more complicated because we now need to deal with conditions. We start by evaluating the condition itself as an expression like normal, and then we're going to evaluate the two sides. So the true side will produce some environment. This is what would be set in each variable if the condition had been true, so we had run the true side. Otherwise, we're going to back up, and we're going to do the same thing for the false side. So we'll see if the condition was false, this is the Python code we would have run, and this is the resulting environment that we would be in. And now we just need to merge them together into a composite environment, which is what's true in either case. And so we just take each variable and say, oh, if the condition was true, then we would be in the left, otherwise it would be in the right, so we wrap them in an if-then-else, and this maintains the original semantics. And of course, they're already equal because our symbolic values don't have side effects. We're just able to leave it alone. And this is usually what happens. Lastly, we need to do with actually returning values so that we're able to extract them out. So in addition to the environment storing variables, it also stores a list of early returns. So if we say if GHI return MNO of X, otherwise, if PQR, return VWX, etc., all we do is maintain a list of conditions with return values. And so again, the conditions are going to be the symbolic value of when this is the case, we return this value. And we just go through them semantically in order and take the first one that returns true. And if none of them do, we have a fall-through environment that still stores the values of the variables that we'd get if nothing had returned. But the result is that we're able to take this code from before and we're able to convert it into an exactly equivalent Velox expression. We've done a lot of work to make sure that we always guarantee that the semantics of the resulting Velox is the same as the initial input Python, but there's no actual Python in the result. And so we don't have to tell people, oh, if you're doing basic arithmetic, don't write it in Python. They're welcome to do it whenever they want, however they want. And so what this gives us is that Python is a DSL, a domain-specific language, for writing Velox expressions. We don't have to teach people about a new kind of thing in order to run the Python that they want to run. They're able to just write Python, and we execute it in a much better format that works much better with the rest of the Velox execution that we're doing. So automatically, there's no GIL, so we're able to run it multi-threaded. All of the heap representations are gone. We're using the same flat vector arrays that every other Velox expression uses, and we also get SymD for free without having to actually tell users that this is even a thing. If they're running multiple rows of input, it automatically will add numbers together in parallel, for example. And then to make this work in general, we have a lot of support for fallbacks. So we have some partial fallbacks where a function, say like date format, we might accept certain types of date formats, but we might have struggled to emulate the error precisely. But the vast majority of code that's flowing through the system shouldn't be generating errors, and so we will assume that usually we'll get a successful conversion. And so in that case, we will dynamically try to run the Python as a converted form. And if we detect we fall into a case that can't be parsed using the formats we expect, then we will fall back and actually run a Python UDF. And so this means there's only Python involved in this rare error case that usually you won't encounter. Some functions we just don't support at all. And so in that case, we still have a Python runtime, so we're able to run things in parallel in subprocesses to do whatever work is necessary. And lastly, we have a gas limit, which identifies certain pathological cases which would either take too much time to compute or just otherwise wouldn't be good candidates to run in Velox due to, e.g., accidentally making code quadratic. But we also support a bunch of other things that I haven't mentioned, such as for loops and mutable arrays, so that, for instance, if you loop over an element, loop over one list and append into another, we're able to turn that into a reduce or a transform or a filter. Yeah, but we're still continuing to expand our library functions for it. So basically, the result of this is we're able to make it really easy for users to define new features and new transformations on features because they just write Python, which they already know about. That's not going to be new to them. But this means that it's automatically fast enough for real-time inference. If they want to do something crazy and import some library we've never heard of, they totally can. But as long as they're doing simple data transformations that are predictable and very Pythonic, they'll be able to run them as Velox expressions without any effort on their part. And so it makes it much more approachable to build these kinds of very complex plans and still let them run in production at scale. So this makes it much easier for teams to iterate. Yeah, I think that's time, so.